The next talk is given by Charlie Macaskill from Sydney on vortex simulations of two-dimensional turbulence in confined domains.
Well, thank you for having me here. I've certainly been enjoying the conference up till now, and I hope I'll keep enjoying it for the next half an hour. But I've called my talk a rather what I feel is a bit over-the-top description. I've called it 2D turbulence, but it's really more about what happens to arrays of vortex patches in confined domains. And I'll try and motivate why I think that's got something to do with 2D turbulence as I go through the talk. So, an overview, and what I want to do is to look at interaction of vortex patches in a number of different 2D confined domains. I'm going to be using essentially the Dritschel and Ambaum contour advective semi-Lagrangian method, which follows vorticity contours in a Lagrangian sense, but finds the velocity to advect those vorticity contours using a grid-based method. Now, recently, in this paper and in a longer version that's been submitted, we came up with a simple self-similar model of what happens in 2D turbulence and checked the ideas using doubly periodic simulations. And these were very high resolution simulations using the more advanced form of CASL that David will talk about in the next session. But specifically, the predictions were that if you had freely decaying turbulence, the entropy should decay at longish to intermediate to longish times, like t to the minus 1/3, which is a result that's been found numerically many times. I think it would be said now, give or take 0.1 in the last 10 to 15 years. Secondly, the prediction was that the entropy spectrum should go like k to the minus 3, and that's really very steep compared to the traditional bachelor view of the entropy spectrum. And finally, that the largest vortex radius in terms of the self-similar part of the spectrum should grow like t to the 1/6. And so what I'm going to try and convince you is that if you consider confined domains of various sorts, that these two results appear to be reasonably robust. The precise mechanism that goes into the self-similar argument may possibly have to be changed a little bit. And I have tried to test this last argument, but there are some difficulties which will become apparent when I get to that. Okay, so the governing equations are very simple. We've just got vorticity is the curl of the velocity. d omega by dt is 0. And to find the velocity at any particular time point, we have to invert the Poisson equation for the stream function. Now, how are we going to try and do this? Well, we're going to try and generalize this method of Dritschel and Ambaum. We are able to solve the stream function vorticity equations in an arbitrary confined domain with an irregular boundary. Although this is not really relevant to what I'm talking about today, the domain can contain arbitrarily shaped islands, if you wish. But the critical restriction is that the boundaries are just supposed to be slip boundaries. So they're not no-flow boundaries. They're where all the velocities are 0. They're just slip boundaries where psi is constant. So consistent with the envisaged type of picture that we're considering. How does CASL work once you extend it to enclosed domains? Well, let's say we know some particular time t and have the velocity at that particular time t, then stepping out of the vorticity equation to the next time point is really essentially unchanged. If you know u, you use the standard method to advect the nodes that make up the vorticity contours. You can continue to use the contour surgery and node redistribution unchanged, which is really nice because they've been in development for 15 to 20 years now. There is a minor tweak here that we have to impose. Small errors can lead to little bits of vorticity escaping from the domain. We need a way of bringing them back in, and there are a number of rather fudgy sort of approaches that can be used. I won't go into any details today, but generally speaking, this doesn't seem to cause any problems, even in quite convoluted boundaries. The critical thing, then, the critical difference, is that the Poisson equation for the stream function in our non-doubly periodic domain has to be inverted. And this just summarizes what you can do. Doubly periodic domains, well, that was just FFTs, which is nice. First case I looked at, other than doubly periodic, was the cylindrical case. And here you use FFTs in the azimuthal direction, finite differences in the radial direction, and of course that can be extended in depth if you wish as well. And we did some calculations like that. Then the general boundary, the idea is you embed whatever your shape is in a rectangular grid. You could still get order delta squared accuracy. The difficulty with the problem is that if you want to go to the 3D problem, where you have separate vertical modes, things can be a little trickier because at the moment I'm storing forever the inverse of the discrete operator representing the del squared. So I'm storing that and not recalculating. If I've got 100 vertical modes, I'm going to have to find a way to use an iterative approach. What you actually will do there, and I have tested this, is you would store the del squared equals, and then if you need to solve del squared plus k squared equals, you iterate from that for small k, or you reshape everything and iterate the large k, and you can do that in just a few iterations. So in general, it will extend to 3D, but that's not the thing today. So I've got a quick example just to show you. This is really just to show that the method works. And this is a kind of problem that's been looked at by, say, McDonald from UCL and Crowdy. And if I can read, which of course I can't, there we go. So let's just a patch. And let's take this back. So we start off with a
fixed island.
That's a fixed island, yeah. So in fact, I have to know what the stream function value is on the fixed island, so you have to use a mapping technique to work that out. But then McDonald, for example, would use a Schwarz-Christoffel approach to do this problem. He can actually solve such a problem without having to embed in a boundary. Here I'm just using a purely numerical approach. So you can do it.
Well, wait a minute, that was a comparison, was it? With the analytic versus the numerical?
The analytic is only semi-analytic. There's no comparison.
It's an independent solution. Can we see the comparison again?
Sorry, no, I haven't shown you. I've only shown you my solution.
Oh, I did.
But his looks the same.
Oh, does it?
Yeah.
Even the fine filaments?
Yeah, he can do, because what he does is he uses the original contour dynamics idea and then maps following nodes.
No surgery?
In principle, he could even use surgery.
But he didn't?
I can't remember precisely what he did, but the details come out really nicely. So, but here we're not doing anything clever. We're just solving the stream function equation at each time step. Okay, so thinking about 2D, this equation clearly isn't right in 2D. There's a vortex stretching term, which isn't there. So we don't have the cascade that you have in 3D, where typically, say, one thinks of forcing at low wave numbers, interaction between vortices leading to vortex stretching, leading to smaller scales, and then all the way down to dissipation, 3D cascade. So there's no direct mechanism for sending energy to small scales. What you do see, though, is generation of high wave number in the vorticity field through interactions of vortices. Now, I wanted to just say a bit about the self-similar idea introduced in the Dritchell et al. Paper. You take a population of vortex patches, and for our purposes, these will all have equal strengths, but they have a distribution of areas. Our total entropy is defined by Q, with spectral density omega, and the energy density is squiggly E. Omega V is the vorticity magnitude, which we'll need in a minute. If you consider only vortices and not the filaments that will arise in any simulation, then you can relate the entropy with the number density of the vortex areas. And since A twiddles k to the minus 2, dA goes like k to the minus 3 dk, and plugging in, you come down to this relation that the spectral density of energy is k to the minus 7 plus 2p. And p is undetermined. And this was a result that was generated by Benzi et al. As long ago as 92.
Is not P1 just dimension?
Well, it in fact,
pretty constantly specified, so it's not.
no, you can't. So you can't. Sorry, I was just looking at whether that was going to be the right answer, but no, it's dimensionally. You've got to allow some freedom in P. You can fix the dimensions up.
So the true answer is not 1.
No, you can play with it. Regarded as a preconst. And that was certainly how Benzi et al. Viewed it at the time. They fit it to data. What we're familiar with is Batchelor's model for 2D, where with dimensional analysis and assuming only that time evolution was given by the initial energy, we get an energy spectrum that goes like t to the minus 2, k to the minus 3. And so, and I guess this is sort of partly an answer to your question, if you refer that back to the Benzi et al. Picture, Batchelor is p equals 2.
This is force.
Doesn't matter. Because I mean, the thing still works. Or doesn't work, depending on how you view it. How do you have freedom to get away from this solution? What freedom do you have to move away from the t to the minus 2, k to the minus 3? A possible counter-argument is that, and this is something that's been seen in a lot of simulations in 2D, vortices are long-lived in 2D, as opposed to 3D, so that the time evolution can be determined by vortex interactions that are local in space, not in wave number. And that makes a significant difference. Now, what we tried to do is to tie this P down, and having tied P down, tie down the time variation as well. So I've jumped to the result here, but on the next page, we had assumed, and this is really the only distribution of A that will give you a self-similar behavior, otherwise you get unbounded problems and so on. N of A is some constant times time, or some function of time, divided by A.
That's what they meant. You
Yeah.
mentioned it.
Yeah, yeah. But in fact, that turns out to be the right choice. If you view P as being something you could choose arbitrarily, well, then you can choose it arbitrarily. If you want it to give you a self-similar result, then you need 1 over A.
That's what dimensional argument is about, giving you self-similar.
Yeah, so it's consistent, yeah. In this case, we get energy spectrum looks like k to the minus 5, not k to the minus 3. And then the entropy will scale like k to the minus 3. How do we go any further? Well, to go further, we now need to say something about this C of t. And this sort of idea was introduced by Carnevale et al. In 1991. But they had a gas of equal-sized vortices. We have a distribution of vortices. And it's easy to show that the energy must scale like Ca to the 4th. Conservation of energy gives C twiddling a to the minus 4. That tells you about vorticity and area fraction. But how do we work out what A does? Well, we expect that A will increase as vortices interact. We imagine we're going to be in a situation where we have a sea of vortices interacting only now and then. The argument we make is that the most likely interaction is dipole-monopole interaction. And here's an example from an old paper by Dritchell and Zabuski, I think on a surface of a sphere. Yeah. Again, invoking self-similarity and requiring that the entropy decays at a rate independent of scale gives us this proposed relation for the entropy associated with vortices only. dqv by dt is proportional to probability of collision times qv over t int, where t int is the time for a dipole to travel to its next calamity. We assume that p col goes like a to the minus 4, which is not a very bad assumption. That's a good assumption. If we really are thinking about dipoles interacting with monopoles, then t int should go like a squared. And this leads to a form here, 1 over a cubed dA by dt twiddles 1 over a to the 8th. What that indicates, though, is that if this t int is a little bit wrong, it's only going to make a small change here. And so the t to the 1/6 might become t to the 1/7 or t to the 1/5 or something. So, however, the t to the 1/6 is critical in the sense that that's the only one that gives you a t to the minus 1/3 for the entropy decay and the k to the minus 5 for the wave number decay. So 1/6 is very important, and we should bear that in mind. Okay, so here's a Christmas tree. It didn't look like a Christmas tree at first, but since I've been here, it looks like a Christmas tree.
Red green, perhaps.
Yeah. Well, yeah, but you know, we've got to have vortices. So let me first just run you through a simulation, just to give you an idea how this goes. And this is the sea of vortices that we're interested in. And if you've got very fast eyes, you might have picked out a few things. But what I've done is I've gone through and just tried to pick out a few occurrences of interest, just to sort of point out the kind of interactions that take place. So around about here, according to me, a dipole hits a wall. So it must be this one. And nothing much happens. Boring. Okay, let's go on to time 40. Now, part of a dipole is broken down at the wall. Aha! This poor chap here is not long for this life. So the wall is now having an effect. This wouldn't take place in doubly periodic domain. 55. So this is a bit of a zoo. Like-signed vortices interact. Those of you with sharp eyes will tell me where that is. Right. There we go. So they had a good time. 95. At 95, oh, now we have a dipole influenced by the peninsula. So here's a dipole. Here it goes. Bang. So the peninsula is playing a role. And then way out at 181, a canonical sort of event. We now have a dipole is going to interact with a monopole. Here's the dipole. The monopole hasn't become apparent yet, but if we just follow this through, here comes the monopole. And there we go. Okay? So there's a number of different styles of interaction that can take place. So the question is, what does the wave number spectrum look like? Well, I've scaled the wave number spectra at different times by t to the 1/3, t to the minus 1/3, the decay that's predicted, and just averaged. And the k to the minus 3 does seem to be fairly ubiquitous. This is for entropy, remember, k to the minus 3. Now, I thought this was a good t to the minus 1/3 until yesterday. And then kinks in spectra started to be discussed. And so now I'm a little bit dubious about calling this anything like t to the minus 1/3, because obviously I've got quite a significant thing here. This is the average of only 8 of 6 realizations. There's quite a bit of variability, but I think it's pretty clear there's a clear trend here. But at longer times, there does appear to be a t to the minus 1/3. I think that's fairly reasonable. Circle, well, I won't show you the interactions with that case, but again, k to the minus 3, t to the minus 1/3, and I might do the gap interaction. This one's sort of quite nice. This gap is not actually, it is about 1 grid point thick, so there's a grid point between the two sides here, and so this is going to give a sharp boundary. Top one, thank you. And I'll just run this one just to show you what happens. One sort of odd thing that happened with a number of these gap cases.
They're going to separate.
It wasn't always true, but most times the two signs of vorticity separated into the two halves of the box. That's right. And I don't. Is that obvious? I don't know.
Scale cascade.
Well, it's negative temperature state, we can call it if you want. That's a name, but
Yeah. So anyway, that doesn't always happen, but it's reasonably robust. Entropy again. Time dependence. Well, now I better get rid of that one very quickly. Now here, unfortunately, there are two things wrong with this slide. The astute student will immediately tell me that I've got my power laws wrong. It should be plus 1/6 and plus 1/12, yes. So, and of course, we want t to the 1/6. And so this was pretty depressing when I got this result. But it was sort of Saturday afternoon at 5 o'clock and the plane was leaving at 9. So, couldn't do much about it. But I think I have the explanation. I think that the vortex that I was tracking is actually outside the self-similar range. I think it's early on in the wave number spectrum. Because I'm looking for the biggest vortices with both positive and negative sign. I'm probably back here somewhere. So I
Must be statement about the average value, which means that there's also probability distribution which works. You don't track one vortex. Something mean must be
I think that's probably right. So just looking at the biggest vortex in each simulation, then averaging is probably the wrong thing to do. But I wasn't quite sure what the right thing to do was. So anyway, I don't think that's a negative really. I think that's just what I got. Right, okay. Conclusions. My claim is that the k to the minus 3, t to the minus 1/3 seem to be reasonably robust. I think I need to do more simulations before I can make that claim strongly, but it seems to be reasonable. The second point is, well, that was depressing, but as we've discussed already, probably not a big deal. The third point is, well, no slip boundaries. This is a little artificial in some cases. Can you deal with, can you deal with no slip boundaries? And Van Heist and Klerks and so on have done a lot of work on this, both experimentally and numerically. We're starting to think that we might be able to get CASL to work in cases where you have a no-slip boundary. And that would be interesting because the dynamics becomes quite different at the boundaries when you have such a boundary condition. But that's next time. Right, so anyway.
My question in first, so the calculations were nominally invisible on the shows, so
Yep.
the dissipation was effectively computational.
Yes, the contour surgery does the dissipation.
That's right. So is that a reason why? So it's not really very well under control. So it might be why
It's a long way out. It's a long way. Typically, the contour surgery doesn't look like it's a problem. Well, I mean, I think we can be guided by the doubly periodic cases. Their contour surgery, despite its black magic sort of cachet, doesn't seem to have been a problem over the years.
some of the wobbles in the
I don't believe so. No. Yep.
I have an idea that the reason why you saw so many dipole wall collisions, and this is a different type of interaction, is that obviously the wall promotes these dipole-dipole collisions, if you like, whereas in doubly periodic domains, it's quite rare to have long-lived dipoles.
Sure.
And therefore, the chance of two of these coming together is quite small. So there are different interactions here. And that could change things here.
Well, that's the issue. Is there some more basic underlying theory for why you get this same kind of scaling? Because it does seem that the actual details of the interactions are different from the doubly periodic case. I'd agree with that.